Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to introduce adaptive techniques for approximating solutions to first-order initial value problems. So in this topic, we will describe adaptive algorithms for finding approximations to solutions to initial value problems. That is, at every single step, we will actually dynamically change the step size to be optimal. Now, we will list the algorithms that we will see in this section, and we will discuss making dynamic changes to the step size, and this is going to include a discussion on the limitations to changes we will accept. Finally, we will discuss appropriate data structures for such adaptive algorithms, and as a hint, it's not going to be just using an array like we could have for the iterative solvers we previously saw. All right, we started by introducing Euler's, Hoyne's, and the fourth-order Runge-Kutta methods. We then determined the error of each, and we then introduced an iterative technique that allows us to estimate the error of these algorithms and to determine whether or not we have sufficiently many points. So what we had to do is we had to approximate the solution with endpoints, and then we had to approximate the same solution with 2 endpoints, and then possibly with 4n, 8n, etc. Now, our error analysis of the original algorithms suggested that the error should drop off according to order h squared, order h to the fourth, depending on the algorithm. However, in all cases, this required us to do a lot of work and a lot of recalculation. So this is an approach we'd rather not take. All right, so we're going to use the following approach instead. Here you can see at time tk, we have an approximation y sub k, which is an approximation of the actual solution at time t sub k. Now at each step, we're going to try to estimate the next value, but we're also going to try to estimate the error of the next approximation. So we're going to calculate the value yk plus 1, but also we're going to try to estimate the error of this approximation. And this will tell us whether or not we should or should not use this particular approximation, and whether or not we should use a smaller value of h, or possibly we could use a larger value of h. Thus, we're going to proceed as follows. Given an approximation y sub k at the point t sub k, what we're going to do is we're going to use not one, but 2 different algorithms, one of which is significantly more precise. Using the same nomenclature from the last few topics, we will denote the not so good approximation as y sub k plus 1, and then we will calculate a second, more precise approximation, which we will designate z sub k plus 1. All right, so now we have 2 different approximations, the first less precise, the second more precise, of the next point. Now, neither z sub k plus 1 nor y sub k plus 1 is exact, because they are both approximations using 2 different algorithms. But if our choice of algorithm is such that z sub k plus 1 is much more accurate, and much more means essentially that the difference between z sub k plus 1 and y sub k plus 1, the absolute value of that difference, is not an unreasonable approximation of the error of yk plus 1. So we calculate that difference, and we will assume that that difference is actually the error of the worse approximation. Now, as with the previous topic, we're going to be a little conservative. We're going to overestimate the error. So we will actually calculate this difference and take the absolute value, but then we'll double it. So this should seriously overestimate the error of the less precise value y sub k plus 1. All right, now you'll recall that the absolute epsilon value is the maximum error we are willing to accept per unit time. Consequently, the maximum error we are willing to accept on an interval of width h is h times this absolute epsilon. So if h is very small, we're not going to accept a very large error, whereas if h is larger, we're willing to accept a larger error over this interval. Now, if the estimation of the error is still less than h times this absolute epsilon, then we're okay. Y sub k plus 1 is a sufficiently accurate approximation of the solution, so we can carry on to approximate the next value. However, if this is false, then we need to try again with a smaller value of h. All right, therefore, we have two possibilities now. The first possibility is that this estimator of the error is less than the absolute epsilon times h. What this says is our approximation is actually too accurate. Okay, that's not bad. We might as well keep the value. But this also says that our step size is too small. Therefore, we could actually use a larger value of h with the next step. Now, on the other hand, if twice this difference is greater than the absolute epsilon value times h, this indicates the error is probably or possibly too large. Again, we're overestimating, but we have to be careful. In this case, we can't carry on because there's too much error in our current approximation. We need to calculate a smaller value of h and then redo the calculation with that smaller value of h. Questions? In the first case, how much larger can we make h? In the second case, how much smaller must we make h? All right, answer. The way that we're going to do this is we're actually going to calculate a scaling factor a. Now, if a is greater than 1, then h can be made larger by a factor of a, so we just continue. However, with the next step, we use a times h. If a is less than or equal to 1, then h is too large. So we're going to try again, this time with a times h. Question. Isn't a times h actually supposed to be the ideal step size? Answer. Actually, it is an approximation of the ideal step size for the current point. And that's a problem if a is exactly equal to 1. But it's also a problem for the next step, because at the next step, the ideal step size may be either ever so slightly larger or slightly smaller, and it's essentially going to be a 50-50 shot. Now, if the ideal step size is smaller, then that means with the next step, we'll actually have to automatically recalculate with a smaller value of h. Consequently, we have one more solution. Before we use this scalar multiple, we will multiply it by 0.9. We will make sure that the scaling factor is only 90% of what we estimate it should be. What this guarantees is that almost never will we have to recalculate, and there is a small cost. we will need approximately 11% more intervals. But that's actually not that bad a cost if we have to minimize the number of recalculations we have to do. Consequently, we will actually look at two adaptive algorithms. In order to introduce this concept and to understand the error analysis, we will begin by using both Euler and Hoyne. Euler will give us the worse approximation, and we will use Hoyne's approximation to give us the better approximation, to estimate the error of Euler's method. This is going to be useful because the error analysis will be much easier, and it will hopefully introduce the material in such a way that you can easily understand what's going on. Having done so, we will then look at a very recent algorithm, one that was first described in 1980, the dormant prince algorithm, one that is used quite often in industry. All right, so throughout this, we're going to be changing the value of h, making it either slightly larger or slightly smaller. However, when we start executing these algorithms, we are going to require some information from the person wanting to solve the ODE. First of all, we'll need a minimum value of h. Why is that? Well, if, for example, the ODE actually has a discontinuity in it, then h is actually going to be forced to be infinitesimally small if we want the accuracy we're looking for. This becomes unreasonable, and consequently, at some point we have to say, all right, this h value is sufficiently small, let's just use the approximation and deal with the error. However, we also need a maximum value of h based on the problem at hand, because after all, if you have, for example, a reasonably smooth forcing function which has a pulse that is of width less than half a second, then if your h value is greater than a second or even more, then there's a good chance that the ODE solver may simply pass over that pulse and ignore it. This is going to cause an issue because now your solution, or your approximation thereof, is not going to be very good. So once again, the user must also specify a value of h that is a maximal possible value that should be used. We also therefore need an initial value of h. Well, to make life easier, we're going to use the geometric mean of both the minimum and maximum values of h. What does the geometric mean mean? Bad pun. Well, for example, suppose that the minimum value of h we're willing to use is 0.001, and the maximum value of h we're willing to consider is 0.1, then the geometric mean of these is 0.01, right between the two logarithmically speaking. Also, while we'd like to use the value of h that is ideal, this also means we're going to be using approximations to change the value of h. Because after all, y sub k plus 1 and z sub k plus 1 are both approximations, and they could both be much worse than we normally anticipate. Thus, we're also going to be conservative, meaning we're not going to ever allow h to be changed by more than a factor of 2 with any subsequent step. And at the same time, if we have to repeat a step, we will not let h be more than halved, because it could be some small fluke that suggests the next value of h should either be too large or way too small, and this is by fluke, not by some unfortunate coincidence between the errors of h of the more accurate method and the less accurate method. So we're going to have to be careful here as well. We will not allow h to be more than doubled, nor will we allow it to be less than halved. Now here's another interesting question. What data structures should we use for these adaptive algorithms? The problem is we don't know how many steps are going to be required. If h needs to be very small, then there will be many steps. On the other hand, if h is very large or can be very large, then we will not require as many steps. So therefore, if we were to allocate an array, it may occur that, first of all, the array is far too large for what we have. Therefore, there's going to be wasted memory and/or time. There's definitely going to be wasted memory. However, if at the end we decide to resize the array and make it smaller, then we're going to have wasted time. If the array is too small, then we must allocate a larger array and then copy everything from the smaller array over to the larger array before we continue. Once again, a problem. The other issue here is that if we were to, say, double the array capacity if it becomes too large, then this may actually also, once again, result in order n wasted memory, especially if we only need a few more entries. Instead, this algorithm requires a data structure that, first of all, allows order 1 insertions with all operations. That's order 1 in time and in memory. Also, it must have order 1 wasted memory at any time. What data structure am I thinking about? A queue. Yeah, something very easy. So, while we are calculating the subsequent entries of the subsequent approximations, we will take the approximations and throw them into a queue. Then at the end, once we know how many points were required, we can allocate memory for appropriately sized arrays, copy all the information over, and send those arrays back to the user. So that's the last thing we will do. We will use a queue, and then we will convert it back into an array. Now, we're not going to be using a queue that dynamically allocates memory with every single step. Instead, we will be using a queue such as the one that is in the standard template library. All right, let's look at an implementation of a general adaptive algorithm. We will return the number of intervals, that is the number of points minus 1, and 3 arrays, the t-values, the y-values, and the derivatives at the y-values. The arguments are the function that defines the right-hand side of the ordinary differential equation, a pair of values being the initial t-value and the final t-value, the initial y-value, the minimum and maximum h values, and the acceptable absolute error per unit time. Now, first we will ensure that the first or the minimum h value is greater than 0, and we will ensure or assert that the maximum h value is greater than the minimum h value. Finally, we will initialize the value of h with the geometric mean of the minimum and maximum h values. Next, we will set up 3 queues, one to store the t-values, one for the y-values, and one for the derivatives at these y-values. We will now push the first values onto each of these queues, the initial conditions, the initial t-value, the initial y-value, and the value of the slope at the initial t-value. All right, so now we will start approximating the solution at different t values. And we will continue doing so until the most recently calculated t value is finally greater than or equal to the right-hand side, or the final t value that we are trying to approximate the solution at. So basically, the second entry of the range. All right, now we have a value of h that we're starting with, but we don't know whether or not it is appropriate. So, for example, h may be too small. That's okay. If h is too small, then whatever we estimate, it will be a more than sufficiently good approximation, and so we'll keep it. But what happens if h is too large? Then the error is going to be too large, and then we have to recalculate with a smaller value of h. So we will assume that h is too large until we determine that h is not too large, in which case we will set found to true, and we will continue iterating this do-while loop until we find a reasonable approximation. So filling in this do-while loop, we will start. We will calculate the less accurate approximation. We will then calculate the more accurate approximation, and now the absolute value of the difference of these two times 2 will be our approximation of the error of y. With this, we will try to calculate a scaling factor a, and that tells us the ideal width multiplier of h that we should have used. Now, if a is greater than 1, that means that the approximation didn't have enough error, which is good. So that means we can use it. The alternative is if our h value is already the minimum possible value that we're allowing, h min. So if h is already at this minimal h size, or the algorithm told us that we should actually be using a larger width or h value, then we're going to keep the current calculation. So our next t value is the current t value plus h. We will push on to the approximation q, the value of z, and the slope at this point will be calculated by calculating f at that point. We will now indicate that the solution was indeed found. All right, so now we're going to come up to the end of the do-while loop, which makes sure that the current value of h was appropriate and updates it, and the end of the loop where we calculate the next t value so long as we have not yet reached the final t value. Okay, the next step is we're going to now multiply a by 0.9. We're going to be a little bit conservative, and rather than having the exact a value that would be just ideal, we're going to ever so slightly underestimate it so as to ensure that with reasonable certainty the next approximation will definitely succeed. All right, so now if a is greater than 2, we will just multiply h by 2. We do not want to multiply h by a factor greater than 2. Similarly, if a is less than 1/2, then we will multiply h by 1/2. And lastly, this guarantees that h is somewhere between 0.5 and 2. We will just multiply h by that scaling factor. Now we make the final check. If h is less than the minimal scaling factor, we will set h to be that minimum scaling factor. And if h is larger than the maximum h value, we will set h to that maximum h value. All right, we've now calculated sufficiently many t values, and we will now return the appropriate result. First, we find the number of approximating points we've already calculated, and that's just going to be the size of one of the queues. And of course, all three queues should have the same size because we've only ever added a new entry to each of the queues at the same time. We're going to create 3 new dynamically allocated arrays of the appropriate size, and then we will start copying over from the queues into these 3 arrays. Having done so, we will return a tuple containing n minus 1, because after all, n is the number of t values, but everything we've discussed up until now has the value being the number of intervals. So we're going to be consistent. We will return n minus 1 and the 3 arrays. Now you may be wondering, why am I using static cast at the top there? Well, the return type of size is unsigned long. So to avoid a warning, I'm just casting the unsigned long as an unsigned int. I am assuming that we are not going to be having an array or so many t values that there would be over 2 to the 32. Following this topic, you now understand what an adaptive initial value problem solver is. You also know that we are going to be using 2 approximations in this solver at every single step. And we will use at every single step the better approximation to estimate the error of the worst approximation. You're aware that we will introduce such techniques with a hybrid Euler-Hoyne adaptive algorithm, one that I came up with, and then we will carry on to describe the Dormant-Prince algorithm. You understand that this will allow us to dynamically change the value of h, but you also understand that there are restrictions to both the magnitude of h and restrictions to any changes we will make to h. That is, we will not allow us to either more than have double the size of h, nor will we less than halve the size of h with any step. You are also finally aware that there are data structures issues with implementations of these algorithms. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!